If you want to understand how chemical reactions happen, then the most important thing to learn is how and why atoms bond together. In this video, you will uncover the secrets of ionic bonding, how it works, and how this process builds the compounds that surround us. But before we get into the how, let's start with the why. In every corner of the universe, atoms are driven by a single, timeless desire: stability. And this is the quest that binds matter together, atom by atom. And one way in which that stability is found is by the giving and receiving of electrons. And the results of this process are all around us, from the rust on a gate to the salt on my chips. This is the story of how opposites attract. This is ionic bonding. Before we get started, there's a basic skill you're going to need to access this course, and that is the ability to write down the simple electron configuration for any of the first 20 elements of the periodic table. So, if you're not sure why chlorine's electron configuration is 287, or why calcium's is 2882, then it would be best to watch my video on electron configurations, which is linked above, before going any further with this video. With that said, let's now look at how metallic and non-metallic elements react together, with the example of magnesium and oxygen. This is a strip of magnesium ribbon, and it's surrounded by molecules of oxygen. And once I give it a little thermal energy to get it started, this happens. We can explain the reaction that just happened by looking at the driving force behind this reaction, which is stability. Metals, like magnesium, tend to react by giving away their small numbers of outer shell electrons to get back to a more stable configuration where they have full shells of electrons. Magnesium starts with an electron configuration of 282. When it reacts, it loses 2 electrons, becoming 2,8. But those electrons don't simply vanish. They must find a home, and they can do that with oxygen. Oxygen has an electron configuration of 2,6. Notice those 2 spaces, which it needs to fill to reach the more stable full shell configuration of 2,8. And so we see that magnesium is willing to give what oxygen needs, and this transfer is complete. But of course, that stability comes at a price. Both atoms were neutral due to the fact that they had equal numbers of positively charged protons and negatively charged electrons. But now magnesium has given up 2 electrons, leaving a 2+ overall charge in their wake. And oxygen has 2 extra electrons, which means that it now has a 2- overall electrical charge. These new ions are the reason we call this process ionic bonding. Of course, this reaction never happens between just one pair of atoms. It happened many billions of times when even my little strip of magnesium reacted. But for every atom of magnesium that does react, we will need 1 atom of oxygen to take those electrons away, and so the ratio of ions in the final compound will always be equal and the same. This is why an empirical formula is needed to describe the new compound, and so we write magnesium oxide like this, MgO. And the resulting ions attract each other to make a vast lattice of alternating charges spreading out in all three dimensions, giving us the final structure of our first ionic compound. The ionic bonding model explains a great deal. It explains why metals and non-metals react, what charges their ions will form, and the ratio of the ions in their final compounds, and even their reactivity trends across the periodic table, as we'll see at the end of this episode. The reaction I showed you with magnesium is just one example. At GCSE, you'd be expected to explain the reaction between any pair of metal and non-metal elements from the first three periods or rows of the periodic table. And you'd then be expected to write the correct chemical formula of the compound that is produced. Now, that's not as bad as it sounds. I'll show you how to do it. But the first thing we're going to need is an easier way to write our process down. We'll go back to our example of magnesium and oxygen. Now, we already know what's in the nucleus of each element, so instead of showing it, let's just write the symbol there instead. Next, remember that only the outer shell of electrons changed, and so we can simplify our diagram by hiding the rest of them from view. For the elements we will be talking about, we will only have a maximum of 8 outer electrons, and so we can position them like this to save time and space. Now, we will need to be able to show which atom has which electrons at the start. So I'm going to replace one set of them with dots and the other with crosses. It doesn't make any difference which one gets the dots and which one gets the crosses. But for simplicity here, I will always give the metal atom the dots to keep things consistent for you. And so this is now my starting point. And here's the transfer. And now we add the charges. Mg gets 2+ and O 2-. But to show that this is an overall charge on my ion, I'm going to put the symbol and the electrons inside a square bracket, and I'm going to put the charge on the outside like this. And we're done. That is the dot and cross model for the bonding in magnesium oxide. Let's try sodium and chlorine. Here's sodium and chlorine. Sodium's electron configuration is 2-8-1 and chlorine's is 2-8-7. Remember, I'm only going to need to show the outer shell, so there's 1 dot for sodium and 7 crosses for chlorine. Sodium has 1 electron to give, and chlorine has 1 space to fill. So here's the transfer, and there's the result, Na+ and Cl-. And of course these will combine to form crystals of NaCl, that is, table salt. That will work for any group 1 and group 7 combination. Have a look at these examples. We've already seen magnesium and oxygen, which is a good example of a group 2 reacting with a group 6 element. But what about this combination? Here, sodium reacts with oxygen to give a greyish-white layer of sodium oxide on the surface. Let's see what happened. Sodium has a configuration of 2,8,1, and oxygen's, as we already know, is 2,6. Sodium has 1 electron to lose. Oxygen needs 2 to complete its outer shell. So what's the solution? Well, 2 sodium atoms for every 1 oxygen. And then we end up with 2 Na1 pluses and 1 O2 minus, which gives us the final empirical formula for this compound, Na₂O. Alright, what about magnesium chloride? Magnesium atoms have the electron configuration 2,8,2, and chlorine is 2,8,7. Magnesium has 2 electrons to lose, but that chlorine atom has only 1 space to fill. This time, we need a second atom of chlorine. And there it is. Now it's straightforward again. We get these final electron configurations and charges and an empirical formula of MgCl₂. Done. Try this one yourself. Pause the video if you need to. And if you got that one right, then you're ready for a whole set of examples which are available on this worksheet. If you run into any problems, please leave a comment below and I'll help you out. By now, you should be able to use the dot and cross model to explain how metals and non-metals bond. One of the true cornerstones of chemistry. But what about reactivity? Well, so far we haven't said anything about how those elements actually react. We know that the metal atom would like to give up at least 1 outer electron, but the truth of the matter is that electrons are bound to the nucleus by strong electrostatic forces between that electron and the positive nucleus. Those electrons, simply put, cannot drift away and they must be taken. So what we actually have is a battle of electrostatic forces between the nucleus of the metal atom and the nucleus of the non-metal atom, the one that is trying to attract them. In situations where the electrostatic force from the metal nucleus is weak and the attractive force from the non-metal nucleus is strong, we will have a very rapid and a very energetic reaction. Understanding the controlling factors of this process is really the core of chemistry, and we will be diving deeper into this subject in the next episode, where we'll use this same ionic bonding model to explore one of the most fascinating patterns in the periodic table, the trend of reactivity down group 1. I'll see you there.